So the first one is something I've already said. I think I already wrote it down. I'm just going to write it down again for completeness. Limit. You guys remember what that means? Good. Right? It's not if. It's if and only if. That's what I keep saying today, right? The limit can only exist at a point if and only if the limit exists and agrees from both directions. Right? So it's L if and only if it's L from both sides. That says nothing about what f of a is. There's no mention of f of a up there. There's nothing to do with it. The limit doesn't care what happens there, just gets really close. That's theorem 1. Theorem 2. This is not used that much, but again, just for completeness. These are all limit f of x and limit g of x exists. It's pretty much at the beginning of almost every theorem about limits that we use. They have to exist in order for these things to happen. How are we doing so far? So it kind of makes sense. If I have one function and there's another, the f, and another function is always bigger than it, then at some value a, the limit here is going to be less than the limit there. I mean, that's amazing.
So,
yeah.
Is that like the problem you just showed with the limits, when one was up here and one was down here?
Not really, because that was a single function. This is two separate functions. So if I have one function that's always more than the other one, then the limit as I approach a point will, of course, be bigger than the other function's limit, right? That kind of almost is like, well, duh. Right? If this function is always at most this one, this limit of this function is going to be at most this one.
Is that all that's saying?
That's all that's saying. Right, so that one's a really silly one. This next one kind of builds on this, and it's the one that's more important. It's the one that's called the squeeze theorem. And it's a kick-ass theorem. All right, let me see if I want to write it also. So now this says, again, the limits have to exist in h of x too, if that shows up, which it will now. So if I have three functions that operate like this, and I always specify, at least near A. We're doing whatever, but if they get near A, they do this. F is at most G is at most 8. Most is at most H. You with me? So that would be this situation. I could have, so here's F, here's G, no Jeff. Which one's the most? H. I'm just going backwards. And G is in the middle. Okay. But the one special point is A. That's the one I'm interested in. So what really happens at A is this. Then the limit as x approaches A of f of x. I mean, this is all this really says. But I'll show you how it's used in practice. Now again, this almost seems too obvious, but you actually have to prove this.
Can you read that bottom part?
Yep. It's basically this with limits. So if f is less than g is less than h, then the limit of f is less than the limit of g is less than the limit of h.
As it approaches A.
Yeah.
Oh, so that's like saying that x is smaller than g is smaller than h?
Yep. Now here's the cool part. And if the limit as x goes to a of f of x equals the limit as x goes to a of h of x equals L. Okay, let me just let you guys suck that in. If the small dude has the same limit as the big dude, well, what limit is G going to have?
The same thing.
That's why it's called the squeeze theorem.
Does that mean they're going to be...
G has to always be between these two. But let me draw this again. at A, H and F have the same limit at A. So here's H, here's F, right? So H is always the biggest dude. You with me? G has got to always be between these two guys. So what's G's limit gotta be at A? If the limit here is L and the limit here is L, then G's limit has got to be L. It's squeezed. It can't be up here because then it's bigger than H. It's not supposed to be bigger than H. It can't be down there. It's squeezed, right? So that's interesting, but then you start to think about it like, well, what the hell would I do with that, Jeff? Besides just tell people, I know a theorem called the squeeze theorem.
That's what I was going to ask, like, how is this?
I love it. So here's a concrete example of this in use, right? Exactly what you want at this moment. I'm going to erase the first two theorems. Is that cool?
That's cool.
And again, you really shouldn't write all this down. It's in the book. So, and it's written better in the book. So here's one example. I'll use the example here. And you start to see what's got to happen with the kind of problems you can use this on. Now look at that function in there. Just look at it. Can I do anything with that? Is there a conjugate? Is there factoring? Can I like denominators? Is there anything you can do to actually do this by hand? And I can't break them apart because the limit as x goes to 0 of sine of 1 over x does not exist. So I can't break them apart. I can't use the product rule kind of in reverse because one piece of it doesn't exist. What's really nice about the sine function in general, though?
It likes y.
I like that. And y is a good dude. But what's nice in terms of the squeeze theorem?
It's always
Sine's got a
maximum,
and it's got a minimum. That's sort of like what this is built on. It's between this and this. So this function, watch. Once you see this in use once, and I'm using more time than I really wanted to on this, but because we're not going to do a lot with this, but it's interesting to see in practice. This function is always between what two things? Well, what's sine always between? Negative 1 and 1. So if sine is negative 1, this function is negative x squared. If sine is 1, this function is x squared. Will you stop right there and let you guys suck it in? This is always in between negative x squared and x squared because this piece is always in between negative 1 and 1. This thing goes insane when you get close to 0, but look, I'm stopping at 1 and stopping at negative 1. I know it's contained between those two values. I don't care that it's going crazy. I don't care. It's between negative 1 and 1. There you go. Go as many times as you want to. So this function is between x squared times negative 1, at least, and x squared times 1, at most.
Does that mean it's continuous? Because of 1 squared.
Well, sine of 1 over x is an interesting problem as far as its continuity, because then you have to look at 0 to see if it actually exists at that point. We're not going to talk about continuity here because I don't even get there.
Okay.
You with me?
Gotcha.
But at every point, this is true. This is like my f, g, h. And what's the limits of the endpoints function? What's the limits of both of these at 0? Limit as x goes to 0, this is 0. Limit as x goes to 0, this is 0. So then the limit as x goes to 0, this has to be 0 because it's contained, right? So that's such a precise place you can use this theorem. It's not used a lot, but it's just such a cool thing to look at and to see how it works. And that's all the time I want to devote to that. Let me not make it sound like I'm letting you out because I'm not. Certain phrases that make people start packing up, and I almost said one of them. All right, you guys semi-decent with that? I think I assigned like one or most two problems with that, but it basically works the exact same way as this. Yeah?
So why is it x squared on both sides? I'm still not sure.
Again, because the absolute least this could be is negative 1. So the least this function could be is negative 1 x squared. And the most is x squared, and that's exactly, now I can use this theorem.
Just time and coefficient.
Right. So if it was sine x, then it would be negative 1 and 1, right?
It's the same thing. Sine of whatever the hell, the absolute most and least it could be is negative 1 to 1. Right? If I mess with the inside, I don't care what the hell I do to the inside, the output's going to have to be between negative 1 and 1. I haven't done anything to the amplitude of sine. Right? Okay, cool. Maybe. And actually, it's another way to look at it. This is kind of like the amplitude, isn't it?
Yeah, that's kind of what
Maybe that's the way you're looking at it. I didn't even look at it that way. But if that's the amplitude of sine, then it goes between negative that and positive that.
Right.
Kick-ass way to look at it. Why not?
Would be like something similar. You use the asymptotes for like tangent or something like that. Do something similar.
I'm not sure how that... Do it again. If you use the asymptotes.
A tangent. So let's say it was tangent to whatever number was in there. You would use the asymptotes as a barrier for your max.
Not quite. Maybe inverse tangent, because then that's contained between negative pi over 2 and pi over 2, right?
Yeah. That's
That would be a similar thing. Anything that's contained,
Yeah.
that's a piece of what you're looking at, that's where you can use the squeeze theorem. There are some other areas you can use it, but it's not used a lot. So that's even more than I wanted to talk about. That's enough. All right. So now I can just say you know the squeeze theorem, and you at least sort of understand it. So the thing I definitely wanted to do before I let you out of here is to talk about 2.4 at least a little bit. In 2.4, I have already scared you about it. So I'm sorry about that. Bless you. Let me see. Yeah, might as well do this. Let's try this out. Let's see what happens here. Now we can all do this, and that's not the point of section 2.4. Section 2.4 is going to analyze limits to death. So that's why I didn't assign a lot of problems out here. But you've got to see this epsilon delta proof. It's an epsilon delta proof. Right? And it's actually kind of a classic proof that you use in other places too. Epsilon and delta are both just numbers that are bigger than 0. So I use epsilon when I want... I say you can pick whatever number you want. It can be as small as you want. And then I say, then this is going to happen. Ooh. So that's basically the epsilon delta proof. So let's get into I'm going to do the concrete first, and then we'll do the theoretical second. All right, so let's mix it up a little bit. So this problem, this section is not going to ask you to calculate limits. Let's kind of start that way. What would you do here? Factor, right? You wouldn't. Please do, God, don't start canceling. Some of you guys want to, the ones go in. No. What's the top become? Little dude, big dude? Yeah, so I don't know if you guys remember. So x, 1 is 1 times 1 times 1. X and 1 go in the little dude. The other two x's. The other two 1s. And the middle guy is the cleanup dude. Plus 1 times x. There you go. That's how you do a cubes. Right? 1 of each, 2 of each, product in the middle. Right? And even got little things. Soap, same, opposite, always positive, if that helps, what the hell? Right? I always try to stay away from those kind of things because I just want it to make sense. Why is that always positive? Because that determines the sign. If that's ever negative, it's going to change the sign to be wrong. Ooh, so that's always positive for that reason. Okay, enough of that. So, of course, what can I do there? Those go away, and what do you get then?
X squared plus x plus 1.
I like it. So the limit is x goes to 1 is 3. Which means, if I wanted to graph this thing, it looks like this, except at 1. Of course, there's going to be a hole there at 1. Right? So if I want to graph this thing, let's see. So at 0, it's 1. Let me do this. How far do I want to? 2, 4, 6, 8, 10, 12, 14. Let's see what happens. So at 0, it's 1. At 1, it wants to be where? 3. It wants to be at 3, and of course, can't get there, poor little dude. At 2, I didn't have to go all that far, I guess. 2, it's 7. Okay. So it's this parabola. The vertex is at negative 1/2 something. So the vertex is down here somewhere. Whatever the hell it is. And then it goes like that. But I'm mostly just curious about this side. Okay, so the whole idea of this section, let me see if I can make this make sense from the very beginning. The idea of a limit, what does it mean? If the limit of a function is 3, if the limit of a function as x goes to some number, if that limit is 3, what the hell does that mean?
That means you're going in the positive and negative direction towards 3. They're never getting there.
So at some point, this function has to get close to 3. Right? It can't get close to 3 and go, no, I want to be at 28 million. And then I can go, no, at some point, it's got to get close to 3 and never get further away than it is currently. At some point, it's just got to get closer and closer to 3. You with me? That's overanalyzing the idea of limit, but...
From both directions.
From both directions. Exactly. I love it. All right, so far so good? Okay, okay. So, what that really means then, here's my 1. That's the major important player here in this whole thing, right? So if I have some... I'm going to love this. I think I've already said this word in here before. Some neighborhood of 1. And in fact, how far away from 1 do I get? 1 away. So, x minus 1 in this case is, let's say, less than or equal to, well, let's say less than 1. I got my parentheses there, so I don't include those. You stop right there and make sure you guys are with me. Is it cool what I wrote here?
Those parentheses are absolute value.
Those are parentheses. These are absolute values. But the strict less than is because I'm not including the endpoints. Is that cool?
All right.
So, for some interval around 1, I must be within so much of the output. Like, what's the output here? 2. I mean, and it's 1 actually. My little 2's off a little bit. It was 1 there, and what's the output at 2? 7. So, this interval on the x corresponds to this interval on the y. Let me just let you guys soak that in. What do you think? So, this goes here. This goes there. So this interval on the x translates into this interval on the y. So if I get closer to 1, how many colors do I have? 2. All right. If I get closer to 1, a little bit closer to 1, what should happen to my corresponding neighborhood?
The interval should,
especially because this is a nice function. The worst function that is, I got to get freaking close to x for this to make sense. But this is a nice function. I don't have to get crazy close. The closer I get here, so now this output is there. This output is there. Now I'm closer to my output value there. All right, good. How are we doing so far? So even the concrete part here is a little bit weird. But does that make sense? The closer I get to x from either side, from above and below, that means my outputs have to be closer and closer to that limit if that really is the limit. And of course we know it is. We just did it. We know the limit is 3. So you can have some really misbehaving function where you got to get stupid close, within 1 over 10 to the 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 10. That's pretty damn close, right? But it's still the same idea. Okay, so this distance here, let me see, the second one I did was like maybe x minus 1 less than half. Is that cool? So somebody help me out. Let's see if you guys can do this. This is a little bit freaky. But for the first one, the number that comes from the x's that tell me how far the x's are apart, that's the delta. That's the delta number. That's how you make a delta. You start from the tummy, and you go out. Right? Never said it that way, but what the hell? Little fat little voodoo dude started his tummy, and go up and around. Can anybody tell me what that corresponding epsilon is going to be, maybe, for the y interval? And the weird question about that is, number 1 is, how do you even correlate those? And number 2 is, I want one value for epsilon, and you're not going to have a symmetric interval. I just said a whole bunch of shit. Let me say it again. Does it make sense? I'm not going to have a symmetric interval around this. This output is 1, right? So let's look at that together. For this situation here, for that, one value of y was 1, and the other value y is 7. And of course, the real limit is 3. So see how in one direction I'm off by 4, in the other direction I'm off by 2. So I want this statement to be a guarantee. You're guaranteed to be within how much if you're within 1 of an input of 1. Let me say that one more time. If you're within 1 of an input of 1, how close are you guaranteed to be to the actual limit?
2.
No, because I could be off by how much?
4.
I could be off by 4, couldn't I? You guys with me? So if I can make this true, then my function, oh shit, here goes more notation. My function is how far away from the limit, at most 4 away from the limit. I'll let you soak that in. I got that exactly from, and you're going to have to do something like this for the homework. Oh yeah. That was a little creepy. Yeah.
So basically the epsilon value is the greatest distance that it can be from the
limit.
From the limit.
From the true limit.
While still being in the neighborhood.
I love it.
Right.
And in reality, the concrete problem I'm doing here is kind of reverse from what you're going to do for the proofs and such. The delta is going to be the smaller. So we'll do one in reverse. It's actually this whole thing in reverse. It sounds fun. So the epsilon is always the bigger one if you're doing it that way. If you're doing it where you start with this and you work back to this, it's always the smaller delta. You've got to be closer to x. Yeah?
Can you say that one more time? I'm just trying to grasp. I know that the 3 came from being, I'm assuming that the 3 came from being the limit.
Exactly.
But why is it negative 3 from the...
Because how do I say the function, the distance between 3 and the function would of course be subtraction. And the absolute value is because I want distance. Right?
Correct.
So I don't want negative values. That's it. I want the function value to be at most 4 away from the limit. And actually a better way to say that, that's not... The function value is at most 4 away from the limit of 3 when the input is at most 1 away from 1. That's exactly how to say what's going on here. So when I am within 1 of a 1 input, I'm guaranteed to be within 4 of the actual limit of 3 for my function values. So if I plug in 1.7, I'm guaranteed to be within 4 of the real limit. That's an even more concrete example of what's going on here. Anything in here will get me to within there, which is at most 4 away from the actual limit. And this, on one level, you're trying to understand what the hell I'm saying. On the other level, some of you got your brain's going, why the hell do we need this shit? Because the way to actually, the true way to prove that this is the limit of some function is to go through this and actually show that this is true. No matter what epsilon you're given, you can always find a delta that will get you that close to the function. That would mean that that's a true limit. No matter how small somebody says, how close somebody says you have to be to the limit, you can always find some neighborhood that will get you that close. That means that's the real limit. So I want you to be 1/millionth away from the limit. Well, there you go. I want you to be 1 million to the millionth power. Oh, there you go. So that's like, shit, that's the freaking limit. If you can do that for any number somebody can spit at you, any number greater than 0, so you can be stupid small, then that must be the limit. Because it's approaching that. That's really what it's saying. Yeah.
Doing this in reverse, we'd be given 2 y values, and we'd have to find what values of x we would have to be between.
Yes, exactly. So we'll do one like that next.
That makes sense.
Okay. I just like to start with this because this is a little more direct. We can actually plug stuff into the function. The other way, you've got to work it backwards, and we actually need a little help with the calculator maybe. Because it's not easy to do that in reverse. Right? How do you make this equal to 7? Well, that could get a little disgusting if you can't factor it or something. Actually, there you could, but Okay. Maybe. So again, they have decent pictures in here. Page 111. And actually, let me show you, they probably have really cool animation too. Oh, yeah. Oh, and whoever I was supposed to look up the code for, don't let me forget, I can put it up here right now. For WebAssign. See if I remember what I might. All right, sweet.
You just click on 175.
I did, thank you. I just started using WebAssign last semester. I'm not used to it, and I'm not used to having 2 in there now either. So thanks for catching that. So sometimes they have, I can play with the, what do you call it? The yeah, thank you, the illustrations. Where's the page?
So 111.
Thank you. That's, so 111. Here we go.
There we go.
That's a very loud button.
Yeah. Oh, Wolframouth, sweet. It's going to want to load. Let's see if this is in. Oh, I love it. So here's the idea. All right, let's see. So we have a function that, as I approach C, the limit is L. All right, so here's my purple function. And sure enough, as I approach C, it looks like C is 5 here. It approaches L. So somebody, here's the idea. Somebody can tell me E. They can, not E, but epsilon. They can say epsilon is 1/10. Epsilon is whatever. So right now, epsilon is 0.99. So then the corresponding, the 2 different deltas, so this is what we were talking about earlier. To be within 0.99 of the actual function value, I'd have to go to here or to there, right? So it's just adding or subtracting 0.99. So I'm within 0.99 away from the function value, the limit. You with me? So if I look over, the green intersects the purple there. So that means that input gives me that output, and that input gives me the other output. You with me?
Anywhere.
So within this, but I want to be able to define one interval. What interval will be a guarantee that I'm within the green bars? If I make it from 5 to 8, if I make it big, 3 big, I got to go 3 down, and then, oops, shit, I'm outside of the green bar. You see that? So it's always got to be the smaller delta. That's what I was saying earlier.
Always smaller delta than more.
To be more conservative, right? For a given delta, I want to make the epsilon bigger so that it actually fits in.
We're given epsilon.
For a given epsilon, you got to make delta smaller, so I make sure that it fit in.
All right.
All right.
Because
Maybe. Yeah.
if you look at it from the bigger side, then you'll be over on the smaller side.
Exactly. If you go the bigger delta, then the other side's going to go too far. You're not going to be within.
Yeah, you're going to be.
So it's somebody saying, give me how far you can get away from the input of 5, so that I'm guaranteed to be within 0.99. So that's why you want to be more conservative, right? Just about 2. So if I make epsilon, so somebody's like, all right, you did that. Let me make epsilon 0.05, right? So now I want to be within 0.05 of the actual limit. Then, of course, what's delta going to be? The smaller one, 11, right? So you got to be within that much. So no matter what somebody tells me epsilon to be, I can always find a delta that works. That means that L is the limit. That is how you prove that something is the limit of a function. Yeah?
So then, would you write, to equate back to this -3 thing, would you write that as f of x minus L is
Okay, cool.
less than
So the way
0.14?
it is right now, we would say when x minus, I don't know if it's 5 or let's just say c, is less than 0.124674. So when that's true,
Where did C come? Oh, never mind.
yeah, it looks like it's 5, but I can't tell. then, Jeff, just stay there. Then the function is going to be within 0.05 of its limit. Now, if I pick the wrong limit, and here's the thing that's always missing from these explanations, and I'm glad I remembered. If I thought the limit was here, at some point, I'm not going to be able to do this process. It's not going to work. If I pick the wrong limit, this is going to not work at some point. Does that make sense?
If hypothetically,
If I thought the limit at C was actually 4, then I don't care how small I make my thing around here, the function values are never going to go around 4, are they? So you see, maybe that, I don't know if that helps out. So if I thought, let me just do this where I can reach a little bit. If I thought the limit was 1, I don't care how small you make this, will the function values that are actually up here ever fit around 1? Will these green bars ever be down there?
No.
Hell no. So that's the part. That's going to quickly tell you that you got the wrong limit. So let me do this. This is the last thing I want to do. We've got a little bit of time left. Because what's really missing right now is, and some of you guys might not realize this is what the problem is you're having, is the theoretical part of this. How do I know I picked the wrong limit? What if the actual limit's 2.9 and I thought it was 2.899999? I don't think it's going to show up on my hand work. So again, this is the same theme. There's so much we can do by hand. Now let's talk about how to really do this in general. I don't have specific numbers. They don't help me out. I got to have this theory. All right. So hopefully you got a little bit of a grounding of what the hell's going on in the background here. This, the proof feels like you're cheating when you do it. But it's a valid method of proof. It's called a construction proof. You construct something to do what you want it to do, and then you go through it forward. Yeah. Oh, really? Oh, poor little dude. Thank you. I got to remember to do this just automatically. Thanks, man. Because if I'm you, I probably want to watch this a few times. Just to see if I actually was speaking English at any point.
Mr. Wall,
Yeah.
I'm so confused on picking the bigger side. Will there always be a bigger side of the delta or the whatever?
You know, if you have a function that's symmetric, like the top of a parabola, then it's always going to be the same. Does that make sense?
Yeah, it's just, I don't know.
So otherwise, you're always going to have one that's closer than the other one just because of the way the function's set up. You're always going to have...
To the x, right?
Yeah, if there's any kind of a slant to it, one side's always going to get further away than the other side would.
It's kind of like the area under a curve type of thing.
Yeah, if I had a straight line even, is another good example, then you're always going to have a symmetric interval. Does that make sense?
Yeah. No.
The minute it has some kind of curve to it, unless it's a parabola where it's like right in the middle symmetric, there's always going to be one side that's further than the other one.
It's a perfect like rainbow thing.
Exactly. All right, what was I going to do? All right. Let me take one out of the... Here we go. Perfect. So I want to prove that the limit as x goes to 3 So I want to point out something. When I do this, you're first going to be freaked out, then you're going to make an observation, and then you're going to have to be careful because this is a very simple function here, right? In fact, we barely get into this idea, to be honest. I don't want to overexpose you guys if this is the only course you need, but I want to show you this in case you're going further. Because you can use this epsilon delta proof on more disgusting functions, and that's where you're going to want to have seen it before so you're not completely blown away, right? So this is a very simple function here. And obviously, I can just plug a 3 in, and I get 7. So this is a nice place to start. We feel good about this already. Yep. Let's just see how this proof works. And it works the same way if it was a more disgusting function, roughly. All right. So what I want to do, I need to find, given an epsilon bigger than 0. So if somebody just comes along and says, I want you to be within 1/100th, 1/1,000,000th, 1/billionth of the right limit. So given epsilon greater than 0, we need to find delta so that when x minus 3 is less than delta. So you with me? So when I'm within that delta of the input of 3, when I'm within so much of the input of 3, my outputs are within this much of 7. When that, then that. Let me just let you guys soak that in. I'm hoping now that we've had some of this concrete discussion backwards and forwards with this stuff, that now when I write this out, it's not that foreign. Right? When I'm so close to 3 on my inputs, my outputs have to be arbitrarily close to 7. Okay. All right, so here's how this works. And again, the first time you see this, and probably the 28th time you see this, it's going to feel like cheating, but too bad. We do a little side work. And actually, I remember my professor, when I first took calculus, he said, I don't even want to see that side work. That's just your side work, and then you write the proof. And the book presents it the same way. They do work, and then they say, proof. And they start using what they just did. So this is called a construction proof. You construct the thing that's going to work, and then you show that it works. Completely legal. So, over here, what do we want to end up happening? I want f of x minus, okay, f of x is 4x minus 5. I want that minus 7 to be less than epsilon. Now, with the nice functions, this is always going to work. The next step, what can you do? I love it. So you get 4x minus 12. What's really the only thing you can do mathematically with 4x minus 12? Factor out of 4. And it's positive 4, so it can come out of the absolute value. Well, now what's special about what's there?
The same requirement for the delta.
So if I solve for x minus 3, I see what to let delta equal. This is the key part that I didn't know how to tell you until right now. So let me let you guys catch up with me. For the really simple functions like lines, this will always happen. You can always recover this. And watch this beautifulness. If you divide by 4, yes, I did just say beautifulness. I never said that before. So what do you want to let delta? Now, we started with what we want to have happen at the end, which is the cheating part. It feels like we're cheating, but we're really not. We're constructing what we want to make delta. And notice, if somebody's able to come over and just say what epsilon, I want epsilon to be 1,000,000 now. I want epsilon to be 1,000,000,000. Oh, screw you. Right? My delta almost has to be dependent on epsilon. What do I want to let delta equal? Epsilon over 4. So if I let delta equal epsilon over 4, I'm golden. And it's kind of like, well, duh, stupid freaking slope is 4, so whatever I plug in has got to be 1/4 of what I really want it to end up to be. So you can pretty much, if I had a 5x minus 5 there, you just make the stupid delta epsilon over 5. So be careful about that, though. I want you to go through the steps so you know how to kind of write this out. Now, here's the actual, I haven't proven anything yet. I haven't proven a damn thing yet. So you're like, good job, Jeff. So now here's where the proof comes in. So given epsilon greater than 0, let delta equal epsilon over 4. Then, when x minus 3 is less than epsilon over 4, so I have to start here, right? When this is true, then this is true. That's why that's not a proof. When this is true, multiply by 4. Recapture the original problem. Let me write that last bit up here. So I just multiply the 4 in. Then I rewrote it so I can't recapture the original function. Therefore, the limit as x goes to 3, 4x minus 5 equals 7. When somebody comes along and tells me an epsilon bigger than 0, it could be 18. More likely it's going to be 1 over a billion or something. I want you to be within 1 billionth of the limit you think it is. Well, I'm able to get there. If I let delta equal to 1/4 of what they just told me, then when I am that close to the input, my outputs are as close as they told me they should be to the limit. So why is this a proof? Oh, I'm just going to...
No.
He's fine? Oh, I'm sorry. Oh, I got you. That wasn't definitive. I'm like, I thought you were saying the camera. All right. Boom, I got it is good. I like that. What was missing from the concreteness was I have to let epsilon be specific numbers. But you can never imagine the smallest number possible. And doing it this way, epsilon could be the smallest number possible. Smallest number greater than 0. Epsilon can be anything greater than 0. So I don't have to do all the let epsilon be 0.1, let epsilon be 0.01, let epsilon be 0.07. I can just, no matter what the hell epsilon is, it works. Again, some of you guys are like, I missed the magic trick. I didn't see the rabbit come out of the hat. I just see a freaking hat sitting there. What happened? And the whole point is, if somebody gives me an epsilon, I know what to make delta because I did the little side work, so that when I'm this close to 3 for my inputs, my output is as close as they told me it should be to 7. Arbitrarily close. That means that the dot is in the right place. It's not offset. I can always stay within the green lines, no matter how close together they make the green lines. Yeah?
Using larger numbers for proof of concept, someone gives you an epsilon of 8, make delta 2.
Yeah. So if they give me epsilon 8, make delta 2, so I can be within 2 of 3. And actually, I'm glad you said that. We have a little bit of time.
Instead of using incredibly small numbers,
we have a minute.
Difficult to use large numbers.
The key here is that no matter how small epsilon gets, and that's actually the key, but to show this to be in a concrete way, if I let delta be 8, or epsilon be 8, then what's delta equal to?
2.
Yeah, 2. Which means if I am within 2 of 3, right, so if I'm from 1 to 5, my outputs will be within 8 of, what was it? Of 7. So from
8 in both directions or 8 combined?
Yeah, 8 in both directions. So now I wrote it down what it's supposed to be. I realized it's supposed to be underneath. -1, 15. Let me let you guys. 8 in both directions. So if I am within 2 of 3, then I have to be within 8 of the output, right? And that's kind of like marrying it with what we did earlier. So sure enough, real quick, what is f of 1?
F of 1, -1,
And what is f of 5? 15. Now, it's just because this is a linear function that is exactly the right thing. Remember I said earlier, it's going to be perfectly symmetric. If this was non-linear, then you'd have one that was longer on one side, and then you would just pick the right one so you'd fit in, right? So in this case, you'd be given the epsilon. You'd figure out what the delta has to be. And actually, here, I'm kind of cheating. I know what the delta has to be. But you'd have to pick the smaller delta so it'll fit. So it'll be more conservative. Okay, cool. Maybe that helps out. Thank you. Yeah?
So this way, this easier on a bigger scale. If you can go super small with this.
Yeah, it's just harder to see. But that's really, the heart of this is to let epsilon get really small.
But that's what the math's for, right?
Yeah. Because I can handle 8 and stuff like that, but I can't handle 1 billion to the billionth
If I
power.
give you like an epsilon of like 0.25, you can just use the math and find out what the delta is going to be.
Exactly.
And the delta is the x-axis, right?
Delta's x-axis, epsilon's y-axis. That's not too bad, right? Yeah.
Did we get through 2.4? Did we get through 2.4?